that total. It's a good chance for us to remind you about verification futures. We had a very successful verification futures last year in Reading, where we had over 300 people. There's actually 200 people on site in Reading, so it was quite a good networking event. Involved over 100 organisations in 21 different countries, 100 people remotely. And we're expanding that this week, calling it European Verification Week. And it's going to be in Windsor, France and Germany. And Harry Foster is going to be the keynote again. Harry Foster for Mentor is going to be our keynote. And he's just released his abstract. So if you go to our website, you'll see it on there.
Right. Thank you, Brian. So welcome everyone. I'm honored today to be sharing the stage with Adnan Hamid from Record Verification and Olivier Haller from ST Microelectronics, two of the companies that, alongside with Mentor Graphics, have been pioneering the development and deployment of graph-based verification. And I'm sure the other speakers are as excited as I am about the topic of today's seminar and of the impact that we're starting to see that this new technology has on the EDA industry as a whole. So these are some of the things I'd like to go through with you today. I want to start by giving you some background to talk about what graph-based verification actually is and how it relates to something we call intelligent test bench automation, how it fits together. Then I want to talk about why we think graph-based verification should be of interest to you, why it's important, what kind of benefits it can provide. Then we're going to look at some of the technology behind this, the fundamentals of intelligent test bench automation and graph-based verification. I want to talk about the role of coverage, how you define your coverage goals and metrics. That's an important part of this methodology. So I was saying I'm going to talk about some of the more advanced concepts. Although we don't have enough time to go into a great lot of detail, I'll just show you some of the more interesting aspects of graph-based verification. Then I'm going to switch gears slightly and talk about how to integrate graph-based verification in an existing verification environment. I'm going to use UVM as an example, although most of this applies to all of the star VM methodologies out there. And finally, I'm going to share with you some case studies and examples of applications of graph-based verification and what kind of results you can expect. So, to start with, intelligent test bench automation is a term or a buzzword that some of you may not be familiar with. It's been around in the EDA world for a couple of years, and as usual, depending on who is using it, it can mean slightly different things. So here's a definition from Gary Smith, of Gary Smith EDA. He's saying that ITBA is the automatic generation of a test bench from a system-level design description. So that's a pretty general or open-ended description. I will also show you another definition that we tend to use in Mentor Graphics, where we're saying that intelligent test bench automation that is aware of the valid test space, the engineer's verification targets within that space, and the current state of the design that uses automation to efficiently achieve the verification goals. So in order to verify a design, we clearly need some kind of model of the valid input space in order to simulate it. And that model has to be derived from the specification, and it can be expressed in many different ways. It can be expressed as a directed graph, like the one you see on the right, or as a set of rules written in a formal rule language, like you see on the bottom. And they're all related to each other. It's just different views of the same model. So the graph itself is not the end goal. It's just an alternative view of the model that we're creating based on the specification. And the graph itself defines the valid test space. So why is this of interest? Why are people turning to graph-based verification today? Well, the main reason we're seeing that our customers are beginning to use this technology is the promise of predictable coverage closures. The designs are not getting smaller, the simulation times are getting longer, and it's harder and harder to get to closure to reach your coverage goals. So because of the algorithmic nature of graph-based verification, it promises orders of magnitude faster time to coverage. I will talk more about that a bit later on, but achieving coverage goals in a reasonable and predictable time is probably the biggest promise of this technology. Another important aspect is reuse, which is of course ever so important. So one of the really interesting things about graph-based verification is that the stimulus model that we're building can be made independent of the test bench environment, which means that the same model can be reused for behavioral modeling system C, for RTL models, even for emulation net lists at the gate level. There's also the possibility to do a horizontal reuse between different projects where standard graphs describing standard protocols can be reused easily between projects. We're also seeing more and more that intelligent test bench automation is applied at the SoC level to do full system verification of whole systems containing processors, graphics blocks, memories, etc., to verify the interaction. So the same graphs that are used to generate stimulus at the RTL level for the hardware can be reused at the SoC level to create high-level scenarios that involves hardware and software interaction. And finally, the productivity improvements that graph-based verification opens up to some interesting automation opportunities. So for example, a lot of the test bench code can be generated automatically by the tools instead of hand-coded by the engineers. It enables graphical analysis by looking at high-level diagrams instead of eyeballing code, graphical debug, and visualization of test scenarios based on the design spec. So how do you go about if you want to create a graph-based model or an ITBA model? Well, normally you start by defining a set of rules, and the rules contains two sections. There is a declarative part, the first part you see on the screen now, that includes the definition of nodes, like the ones you see up here, create item, do item, etc. And these nodes are linked to tasks or functions in the test bench. There's also declaration of variables that can take different values. So the variables and the range are defined up here as meta actions. So in this case, in this example, you have probably seen already that this is an AXI burst transaction that we are defining. So besides the basic action like creating a transaction, we have variables like burst size, access mode, burst type, burst length, and so on. And then the second part is called the grammar, where we define the abstract behavior. So that's the code at the bottom here, and this would typically replace the procedural code written to create directed tests or constrained random constraint code that you would find in a constrained random test bench. As it says here, most often it contains decision trees, and it's built up of sequences of these nodes and variables that you saw in the declarative part. Optionally, you can add constraints, algebraic constraints as well. I'll talk more about that in a moment. And one important point to note here is that, as you can see, the rules are very implementation independent. All we have done here is described at a very high level an AXI transaction. We are not talking about how that transaction is going to be communicated to the DUT. Once we have defined the rules, we can compile them and visualize them into a graph, as the one you see on the right-hand side. So this graph now graphically depicts the behavior of the protocol or the interface that we are describing. It can be hierarchical. As we can see, there are two branches here. We can do either single burst or multiple burst operations here in the two branches. One important piece of information that we can get from the graph now is the sizing of the stimulus space. So if you look carefully, you see these tiny blue numbers in the graph. This tells us that the total size of this graph here is 864 total combinations. That's our total input space. In this particular subgraph that we see down here, there are 108 possible combinations in total. And that information helps us to assess how much simulation we're going to need in order to reach our coverage goals. The next step is to define our coverage goals using a so-called coverage strategy that defines the goals and priorities. And the coverage goals can be of two types. Either we define what is called a path coverage, which defines typically combinations that we're interested in, combinations of variables and nodes in the graph. So in a way, it's equivalent to a system Verilog cross coverage. So in this example, you see this blue box that sits in the middle of the graph that defines the combinations of access mode, burst type, and burst length that we're interested in covering. The second type is called node coverage, and this is for an individual variable like burst size down here that has 8 possible values. So we're interested in covering those values. So in a way, this is analogous to a system Verilog cover point. And once we have defined this, again, we can see the size of the different objects. So the path coverage has 108 valid combinations. The node coverage has 8 valid combinations. It gives us information about how much simulation we can expect to run. The final step now is to integrate our graph, our compiled graph, with the rest of the test bench. And that's certainly one thing that we have learned over the years when we have helped customer implement this technology. That's that this integration has to be done in a non-intrusive way. Most companies today have spent a lot of effort and time and money building up a verification environment. And whatever new technology that we introduce has to work seamlessly within that environment. So I will talk more about that later on when we get to talking about the UVM integration. But for now, it's enough to know that we can plug into pretty much any simulation or verification environment using standard methods. So in this case, we just create a system Verilog wrapper for our compiled graph. And the wrapper gets loaded into the simulation together with the rest of the test bench and a small runtime component that is used to systematically traverse the graph during simulation to produce stimulus. Once we're up and running, we can use the graph to debug any problems we see in the simulation. We can set breakpoints and single step and so on. So let's step back and talk a little bit more detail about coverage, which is a very important part of this. So as I mentioned at the beginning, the rule graph itself defines the entire valid test space or stimulus space. If we just start simulating that and start to traverse the graph without any goals, the traversal will be random. During simulation, we're going to pick one possible path through the directed graph and produce stimulus according to the sequence that we get. And then we're going to pick another one randomly, and there will certainly be repetition. So we will repeat the same patterns many times if we run long enough. So in a way, that result is equivalent to what you would get using traditional constrained random generation. Once we define our coverage goals, the purpose of that is to direct the tool towards the goals and priorities that we have. So we define the areas of interest, as you saw, the variables and the crosses that we're interested in covering. And once we have done that, during simulation, we are going to systematically produce exactly the stimulus that is needed to cover those goals. And that's where this n times natural logarithm of n advantage comes from that we saw on one of the earlier slides. So it's important to realize that you can use any balance between coverage-driven systematic generation and random generation depending on what your coverage goals are. So let's take a moment to look at some of the more advanced concepts and possibilities that graph-based verification offers. So many modern designs have a very large sequential depth and many internal states that are very difficult to reach and cover using just constrained random generation. So many times you have to fall back to writing complex directed tests to hit those internal states. So in order to reach those states, the test bench has to be adaptive. It has to be able to react based on the internal states of the DUT and the test bench itself. So some of the things we can do with graph-based verification is that we can use DUT state as one of the variables. So instead of randomly selecting or generating a value, we can pick up a value from the DUT itself. So in this example here, it's kind of hard to see what I'm doing here. Let's see the cursor right here. We see a so-called meta-action import, which is picking up an internal state called mode from the DUT. The mode variable is then used in the graph to the right. These trapezoid shapes that you're seeing in the graph here are actually constraints. It's kind of hard to see here, but the constraints are using the mode variable to gate the different branches of the graph. So depending on the state of the DUT, the value of the mode, you're going to select different branches of the graph, and the graph is going to provide different behavior and different stimulus. So this is just one of the possibilities that we enable with graph-based verification. So now I want to shift gear a bit and talk about how we can integrate this and take advantage of graph-based verification in an existing environment. And I'm going to use UVM as an example, as I know that many of you are already familiar with UVM or already using it. But the same information applies to OVM and most of the other star VM methodologies. So we have done similar kinds of integrations with many different environments, ranging from VHDL test benches with directed tests up to OVM, UVM, and even E environments. So in a typical UVM environment, we have a sequence that defines stimulus generation by using some kind of combination of directed tests and constrained random generation. And the sequence produces sequence items that are sent to a sequencer, which then passes them on through a TLM interface to a driver, which provides the pin wiggles to the DUT. That's pretty basic UVM. Now it turns out that all we have to do to take advantage of graph-based verification is to replace the standard sequence with an ITBA sequence, which is now directed by the graph instead of randomly generating stimulus or using procedural code. The rest of the test bench stays unchanged. So from the outside, the ITBA sequence looks just like any standard UVM sequence. It has the same TLM interface. It relies on the same methods like start item, finish item, etc. to send data to the sequencer. So for the rest of the test bench, all the drivers, monitors, scoreboards that you already have will work as normal. There is no change whatsoever. So the steps you normally go through to achieve this is that you start by identifying the target sequence item or items, because there can certainly be more than one sequence in your test bench that you want to run. You then describe the whole stimulus domain, the valid input space, using a graph and rules, as I described to you. Define relationships, possibly using constraints. Then we define the coverage goals. As you have seen already, you define the areas of interest, the variables that you want to cover, the ranges, the crosses, etc. And then you just start the sequence from a normal UVM test, just as you would start any sequence. So let's look at a simple example. We have a very simple bus protocol here that has a 32-bit address and a 64-bit data bus, and it supports burst mode, up to 16 bits bursts. And the starting point here is a simple UVM sequence item that describes all the variables in the transaction. There is an address, there's an access type, which is read or write, the size, and the burst length. So the first thing we need to do is to declare a graph variable for each of the item fields. And it turns out that there's a very simple one-to-one mapping between random variables in your UVM class and the nodes and variables in a rule set like you see here. So all of the variables in the random variables in the sequence item are translated now into the rule file you see to the right. And indeed, this translation can be done automatically because it's very straightforward. There is also some constraints associated with this protocol. So the address must be aligned to match the transfer size, and burst transfer bits can only be 32 or 64 bits. So there are several ways we can accommodate that in our graph. We can either use branches to separate out the different cases that we're interested in, or we can use algebraic constraints. And I will show you examples of both here. So the first constraint here, that the address must be aligned to the transfer size, is described by this constraint that we're seeing inside the box here. So this, as you can see, is very similar to a system Verilog constraint. It actually uses almost exactly the same syntax. So many times these can just be reused from your existing test bench. The other constraint, that when we're doing a burst transfer, each bit can only be 32 or 64 bits, is handled down in this branch down here. So you may see that we have a select operator here in the middle that selects between bursts and non-burst transfers. And when we do a burst, we simply constrain the size to be 32 or 64, while it's unconstrained when we're doing non-burst operations, so it can be any legal size. And again, as I mentioned, the constraints can many times be reused from your existing UVM test bench. Once we compile the graph, it will look something like this. So we can immediately recognize the two different branches where we do burst and non-burst operations. We select the size, the access type, etc. So it's a very easy, understandable view that can be used for code review, for example, instead of just reading through the code. Then the graph has to be integrated into the sequence. And I mentioned at the beginning that all the nodes and variables are linked to tasks or functions. And in the case of UVM, this is actually very trivial. So the tasks that you see to the right that are mapped to all my variables simply assign a value that is assigned under the graph control during simulation. So this trivial code can actually be generated automatically. There's no need to handwrite it. The next step is to define our coverage goals. And in this case, there's a couple of things we're interested in covering. We want to divide our address space into 64 ranges. Naturally, we don't want to hit every single value. That would take forever. So we're going to use bins, just like you do in System Verilog, to divide the address space into 64 discrete ranges. And we want to hit each one of them exactly once. Secondly, we want to cover all the valid combinations of the transaction parameters like access type, burst length, size, etc. So we simply define a path coverage, again, the blue box that you see on the graph, that covers the variables we're interested in crossing. And optionally, you can set priority and the hit goal count, how many times you want to hit it. Down at the bottom, we have a node coverage, a cover point that is covering the 64 bins for the address. And as soon as we have done that, we can do some pre-simulation analysis and figure out how big are these goals, how long is it going to take us, are we going to have to simulate for 10 months before we reach it. And it turns out that in this case, the size of the address is of course 64 because it's 64 bins. That's pretty obvious. The second one is a bit trickier, especially if you have constraints involved, but we can see that the size is exactly 68. So when we run simulation, we're going to work at both of those in parallel. So once we have covered the 68 cases in the cross, we have also covered the 64 ones. So we should be able to complete this in just 64 cycles, 68 cycles, sorry. Finally, we need to integrate this in our existing UVM infrastructure. And as you have seen, the graph-based sequence is just like any other UVM sequence. So depending on your testbench style, you just use the UVM standard methods to include the sequence in your sequence library. You can either use the factory, as you see in the first example here, where we simply do a factory override to select the graph-based sequence instead of the default random sequence. So it's just a single line we need to change in the existing test bench. Alternatively, you can do, as we do in the second example here, where we are explicitly creating and starting the graph-based sequence. So it's really up to you what kind of testbench style you use. But the important thing is that there's nothing special about this. This is just using the standard UVM methods. So ITBA and graph-based verification has been around for a few years now, and it's been successfully applied to a number of different fields and types of verification. We have seen it being used for things like architectural exploration. People use it to do performance characterization or verification of behavioral models. Perhaps the biggest usage is in IP or block level verification, where it works extremely well for bus protocol verification, interface verification, where you have a clearly defined interface. It's a very straightforward task to create a graph that describes a protocol. And many times there is already a graph in the specification that you can base your model upon. We're also seeing a lot of success with SoC integration, where graphs is a great way to model high-level interaction between different subsystems in an SoC, scenarios involving both hardware and software interacting in a complex way. It's very hard to capture using constrained random. And finally, processor verification. I've been personally working on a project where we used graph-based verification to generate streams of instructions for a custom DSP processor that needed to be verified. So this diagram here shows the advantage in coverage closure that is possible using graph-based verification. So this is an internal example that we have. It's a floating point unit that we are verifying using constrained random and a graph-based model. And this FPU, of course, has different operators and operands, so it has 5 different operators and 2 operands. And in order to cover all the valid combinations and sequences, using constrained random, we needed 385,000 tests to get to 100%, while the graph-based model, where we had defined the coverage goals, as you have seen today, needed the theoretical minimum, which is 1,906 tests, which is the actual minimum needed to cover all combinations. So this is the green line. And the thing to notice is that it's completely linear. That's because there is no redundancy in the generation of stimulus. So depending on the application, we typically see at least a 10x acceleration in coverage closure. In some cases, it's orders of magnitudes. So I'm not going to go through all these case studies with you, but I'd just like to highlight that these are some of the projects where ITBA and graph-based verification have been used successfully over the past few years. As you can see, it ranges from applications like consumer electronics to wireless switching, processors, and so on. And in every one of these cases, we have seen either much shorter time to coverage or much higher coverage. And in the green boxes that you see, we actually get both. We get much higher coverage and in much shorter time. So this is my final slide. So summarize what I've seen so far. We have seen that graph-based verification and algorithmic generation enables fast, efficient coverage closure, and it's a great way to describe high-level test scenarios. Graph-based verification really eases reuse, both vertically, as you have seen, because the same sequences can be reused from RTL to up to high level and down to netlist level, because the graph can be made implementation independent. And it also encourages reuse from project to project for the same reasons. And as I hopefully have shown you, it's very easy to integrate into an existing environment, like for example OVM or UVM. So that was my final slide. Are there any questions about this at this time? Yeah, it is, I would say, it is 99% system variable.
Staffan?
Stefan? Yes?
My apologies. Could you re-ask the question for the benefit of remote access users, please?
Sorry. Yeah, the question was about constraints in the rule sets. Why didn't we make them 100% system Verilog, which is a good question. And my answer is that it is extremely close to system Verilog today. I would say it's 99%. The reason is that the rule language itself isn't system Verilog, so there were some minor syntactic differences, which usually has to do with things like where you place the semicolon or not. But in almost every case, it's just a matter of copying and pasting your existing system Verilog constraints. And the goal is that they will be the same. But the rule language itself is not system Verilog. Well, after compiling, the result of the compilation is an internal representation. It's a directed graph.
Staffan, my apologies. Could you repeat the question before you answer? Thank you.
The question was, after you compile it, are the constraints translated to system Verilog? Yeah, there's the short answer and the long answer. The short answer is that the result of the compilation is an internal representation. It's a binary model of a directed graph that contains both the rules and the constraints. It is actually possible to export constraints as well once you have defined them, as well as a coverage model. But the internal representation is a binary representation that can be visualized using the graphs that I've shown you. But there is no, the output is not system Verilog, it's this binary model that is traversed during simulation. Does that answer your question? You can. It actually works with any logic simulator that supports standard PLI or...
Staffan, my apologies, we don't know the question that you're answering.
Oh, sorry, I keep forgetting. Yeah, the question was, since the model is compiled into an internal binary format, does it only work in the Mentor environment? And the answer is no. Although this compiled model is a proprietary format, it's using open interfaces to communicate with the simulator. So it works with pretty much all the simulation environments on the market, not just the Mentor simulators. Yes, the question was, since we do export constraints, if I could elaborate a bit on that. And we can export both the constraints and the coverage model in regular system Verilog, so you can reuse them in your test bench in other ways. There is also a constraint solver that we provide that allows you to examine your constraints without running simulation. So you can, for example, see if you have created contradictions in your constraints that makes them unsolvable. You can find that out before simulation. No, this is a different constraint solver. Oh, sorry. Yeah. The question was, are we using the same constraint solver as a simulator? And the answer is no. Our runtime environment that we're using has actually several constraint solvers. And the reason is that the type of constraint solving we're doing is slightly different than what a simulator does. This is done statically in a different way, so we can't use the one that's built into the simulator. So the question was, the coverage model that we create, is that generated automatically, or how is it generated, and how is coverage information collected? Is it collected by using system Verilog or something else? So there's really two questions. The coverage model that I showed you using node and path coverage can be created in two ways. Either manually by the user, you create it graphically in the graph by creating these path coverage objects and such things that I showed you. So it's done directly by the user. The other alternative is if you have an existing coverage model written in system Verilog, we can extract that and translate it into a coverage strategy that we can use. During simulation, we don't collect coverage information. It's kind of the other way around, that the coverage goals is what actually drives the generation. So during simulation, we will look at each coverage goals and then calculate what stimulus is needed to hit that goal. So the tool will report coverage as it hit cover points and path coverage, but we don't collect coverage in a traditional way. But as I mentioned, we can export the coverage model as regular system Verilog, so you can include it in a monitor in your test bench if you like, and look at the system Verilog view of the same coverage if you so like.
Staffan, that's great, thank you. Staffan, that's great, thank you. We're running short on time to cover all the questions we've got in the various locations. We're actually going to switch to Bristol for questions now, if we may. Mike Bartley.
Sorry.
Can you hear me? Okay, the first question is from Jeff Barrett of Broadcom.
Hi, Staffan. If I've understood correctly from all the examples that you've shown, your coverage metrics have been annotated onto the graph which describes the protocol. Now, in practice, what I find a lot of the time is that you're actually defining your coverage metrics in terms of aspects of the design itself. So in that case, it seems you didn't have such a direct link between the graph that you're running around to generate the stimulus and your prediction of what the coverage would be. So does it work as well when you've got implementation-based coverage metrics?
So yeah, the question was that the coverage model is kind of separated from the DUT. I guess that's what you're referring to, that since the coverage model is kind of overlaid onto the graph, it's not part of the regular coverage metrics model. And I would say that if you do have coverage metrics defined, if you have a test plan where you have your coverage goals, that would be an excellent starting point to create the coverage model for your graph. So you would look at the coverage goals in your test plan and create the coverage model based on that. So it would be just two views of the same thing.
Another question in Bristol from Fabio Bruno.
So my question is, the two main advantages of random coverage-driven verification are coverage closure automation and randomness, really. So the more you run, the more likely you are to reach unthought of scenarios. So by reaching the coverage closure 10 times faster, you risk to have 10 times more bugs left in the design when you ship it.
That's a very good point. Yeah, the question was if we are able to reach the coverage goals 10 times as fast, we run only 1/10 of the simulation, so we risk missing bugs. So there will be more bugs left because they were missing. Maybe the coverage model was incomplete. I guess that's the main concern. And the answer to that is yes, you are correct. If the coverage model is incomplete, the tool is going to generate exactly what you specified, so we are going to miss whatever is not in the coverage model. So in reality, what most of our users do is that they use this systematic approach to reach the coverage goals much faster, and then they use the remaining time to default into random mode. So they run as much simulation as before. It's just that the first priority is to cover the goals that they have specified, and then they just run random and hope that they will hit some random combination that was not part of the coverage model.
Okay, that answers the question from Bristol. There's one remote question, Staffan, from Mukesh Lahori. Do we need a separate license, or does it come with Mentor Simulator Quest System?
Well, that's a more commercial question, but you can actually do it both ways. That we do have something called Questa Ultra, which is a bundle of our simulation environment, Questa and InFact, and some other things. But if you're not a Questa user, you can also get this separately as a separate product without Questa if you want to use it with another simulator.
And one more remote question from Guy Mussenson. Seems coverage is only the input space, is only on the input space, no access to coverage of output and internal state. Is that right?
So the question was, is coverage only on the input space and not on the outputs and internal states? That's not entirely true, because on one of the slides I had this thing called a meta-action import, if you recall, where we had a device that had different modes. So we can actually look at internal states in the design and modify the behavior based on that. So you can create coverage goals that are depending on internal states in your design and target those as well.
Okay, I think we're going to go over to Grenoble for just check if Olivier's got any questions. Okay, we assume there's no questions from Grenoble. Okay, so thank you very much, Staffan.
Thank you very much for listening.